I'm Alex Turner. I'm a new professor in the Department of Atmospheric Science here at the University of Washington. And my research areas are on the carbon cycle and atmospheric chemistry. And I mostly use things like remote sensing and inverse modeling to study these research areas. I'm interested in questions that are at the intersection of climate change and air pollution primarily. And a lot of what motivates my work is understanding the processes that control the abundances of major greenhouse gases. So methane and CO2 are the two strongest anthropogenic radiative forcers, and together account for more than 85% of the greenhouse gas forcing since pre-industrial time. So understanding how these molecules will change, how the abundance of these molecules will change going forward is profoundly important for understanding the future state of our climate. And what I'm showing here are the CO2 concentrations measured at Mauna Loa going back to the 1970s and 1980s. And for CO2 on the top, we see a pretty much monotonic increase with a strong seasonal cycle from the biosphere. Methane, on the other hand, had increasing concentrations from the 1980s through the 1990s until right around 2000 when concentrations stopped rising. Then in 2007, they began rising again. And there's been quite a bit of debate on this, but the processes that are controlling these abundances in atmospheric methane really aren't that well understood. And so a lot of my work has really tried to focus on better understanding what's driving this. An example of questions I'm interested in are things like, what are the processes driving trends in atmospheric methane? What is the role of chemical feedbacks on these abundances? For example, how does variations in ENSO affect these methane abundances? And then also, how has and how will the carbon uptake from the biosphere respond to changing climate? So how does, for example, drought or perturbations from fire impact the biosphere, and what does that mean for our carbon uptake going forward? And then finally, can we use things like satellites to find large methane sources and potentially reduce those emissions and help curb future climate change? So some of the tools that I use in my work are atmospheric modeling and satellite remote sensing. And I typically use them in sort of a Bayesian inference framework to try and better improve our priors or our baseline understanding of these molecules. So yeah, I'm really excited to be a part of the University of Washington and part of the program on climate change. Thanks.